Internal forced convection. This topic discusses forced convection heat transfer inside enclosed passages, such as pipes and ducts. The main focus is how the fluid flow develops from the inlet until it reaches the fully developed condition. In internal flows, velocity and temperature profiles change along the flow direction. This phenomenon is very important in the design of heat exchangers, cooling systems, and piping systems. The analysis combines concepts from fluid mechanics and heat transfer.
Lesson Plan: Heat Transfer. This chapter is placed within the overall structure of the heat transfer course covering conduction, convection, and radiation. Internal forced convection logically follows the discussion of external convection. Each previous chapter builds the conceptual foundation to understand flow and heat transfer behavior. With this structure, students can see the relationship between topics in a systematic way. This chapter becomes an important bridge toward the discussion of heat exchangers.
Learning outcome. The learning objectives of this chapter are to understand flow behavior and heat transfer inside pipes. Students are expected to analyze velocity and temperature profiles. The concepts of hydrodynamic and thermal entry lengths are important parts of the discussion. In addition, the relationships between friction factor, pressure drop, and Nusselt number will be mastered. All of these form the basis for piping system and heat exchanger calculations. Pressure capacity of circular versus non-circular pipes. Circular pipes can withstand high pressure because of the uniform stress distribution. In contrast, non-circular ducts are more prone to deformation when pressure increases. Therefore, circular pipes are more suitable for high-pressure applications. Non-circular ducts are usually used in low-pressure systems. This mechanical consideration is very important in selecting the duct geometry. Velocity profile in laminar flow. In fully developed laminar flow, the velocity profile has a parabolic shape. The maximum velocity occurs at the center of the pipe and becomes zero at the wall due to the no-slip condition. The average velocity is smaller than the maximum velocity. For laminar flow in a circular pipe, the relation V average equals V max divided by 2 applies. This profile reflects the dominance of viscous effects across the entire cross-section. Temperature profiles in tube flow. The actual temperature profile inside a tube is not uniform because of heat transfer from the wall. To simplify the analysis, an idealized uniform temperature profile is used. The mean fluid temperature is defined so that it carries the same energy rate as the actual profile. With this approach, the energy balance remains valid. This concept is very important for internal convection heat transfer calculations. In heat transfer analysis, the actual temperature profile is non-uniform due to heat transfer from the wall, while the idealized temperature profile is uniform, simplifying analysis while preserving the energy transport rate. Hydraulic diameter insights. For circular pipes, the hydraulic diameter is equal to the physical diameter. For non-circular ducts, the hydraulic diameter is defined as 4A over P, where A is the cross-sectional area and P is the wetted perimeter. This concept allows the same correlations to be used for different duct shapes. For channels with a free surface, only the walls in contact with the fluid are counted. The hydraulic diameter unifies different geometries into a single analysis framework. Transitional flow characteristics. In the transitional region, the flow can switch between laminar and turbulent. Die traces show behavior that is sometimes smooth and sometimes erratic. This condition reflects flow instability at intermediate Reynolds numbers. Transitional behavior is very sensitive to small disturbances. Therefore, this region is difficult to predict theoretically. Velocity boundary layer development. Near the inlet,
The velocity profile is initially almost uniform across the cross-section. The velocity boundary layer starts to grow from the wall due to viscous effects. As the distance increases, the boundary layers meet at the pipe center. After that, the velocity profile no longer changes in the axial direction and is called fully developed. The length of this region is called the hydrodynamic entrance length.
Velocity boundary layer development. In flow entering a pipe, the core region is initially nearly irrotational, with a relatively uniform velocity distribution. The velocity boundary layer starts to develop from the wall due to viscous effects. The velocity profile gradually changes along the flow direction. After a certain distance, the profile no longer changes and reaches the fully developed condition. For laminar flow, the final profile becomes a stable parabolic shape.
Correct answer, B. Parabolic velocity profile with maximum velocity at the center. Explanation of incorrect options. A. Uniform velocity profile throughout the pipe cross-section. This describes the initial core region with a uniform velocity distribution, which is observed before the boundary layer starts developing. It does not represent the fully developed laminar flow stage. C. Velocity gradients restricted to the pipe walls with zero velocity at the center. This is incorrect because in fully developed laminar flow, the velocity is highest at the center and decreases toward the walls due to the no-slip boundary condition. D. Flatter velocity profile resembling turbulent flow due to increased mixing. This describes the velocity profile of turbulent flow, which is fuller and flatter compared to the parabolic profile in laminar flow. Mixing is not significant in laminar flow. Thermal boundary layer development. The thermal boundary layer starts to develop when there is a temperature difference between the wall and the fluid. Near the inlet, the temperature profile is still relatively uniform across the cross-section. As the distance increases, temperature gradients form and become more pronounced. In the fully developed region, the shape of the temperature profile no longer changes along the flow direction. Heat transfer is most intense in the entrance region because of the large temperature gradients. Flow and heat transfer in tubes. In the entrance region, the friction factor and the heat transfer coefficient are higher. This is caused by the development of velocity and thermal boundary layers that are not yet fully established. After the fully developed condition is reached, both coefficients become constant. For fluids with high Prandtl numbers, the thermal boundary layer develops more slowly than the velocity boundary layer. This behavior strongly influences the design of the effective pipe length. Nusselt number variation. The Nusselt number has a very high value near the inlet because heat transfer is very intense. As the distance increases, the Nusselt number decreases and approaches a constant value. This value depends on the Reynolds number, where higher Reynolds numbers produce larger Nusselt numbers. Boundary conditions of constant wall temperature or constant heat flux result in slightly different trends. In the fully developed region, the Nusselt number reaches an asymptotic value. Nusselt number variation. The variation of the Nusselt number reflects the development of thermal conditions inside the pipe. At the beginning of the flow, the effect of thermal boundary layer development is very dominant. After that, the contribution of axial changes becomes smaller. The Nusselt number eventually depends only on the flow condition and duct geometry. This behavior forms the basis for using empirical correlations in practical calculations. Heat transfer in flowing fluids is equal to the increase in its thermal energy. Mathematically, this relation can be written as Q dot equals M dot times Cp times Te minus Ti. The inlet and outlet temperatures determine how much energy is absorbed or released. The mass flow rate also directly affects the heat transfer rate. This equation is the foundation of almost all heat exchanger analyses. The heat transfer to a fluid is directly proportional to the temperature difference between the inlet and outlet. The mass flow rate and the specific heat of the fluid. Temperature variation in tubes. Under constant heat flux conditions, both the wall temperature and the fluid temperature increase linearly along the pipe. The difference between the wall temperature and the mean fluid temperature remains constant in the fully developed region. In the entrance region, this difference is larger because the thermal boundary layer is still developing. This behavior simplifies the analysis because the axial temperature gradient is constant. This model is widely used in engineering applications. The analysis is performed on a small control volume element along the pipe with length dx. Heat enters the fluid from the wall through a differential surface area. The mean fluid temperature increases by dTm along this element. The energy balance states that the heat input equals the increase in fluid energy. This differential approach forms the basis for deriving internal convection heat transfer equations. Fully developed temperature profile. In the fully developed condition, the shape of the temperature profile no longer changes along the flow direction. Even though the shape remains the same, the mean fluid temperature continues to increase axially. This happens because the heat flux from the wall is constant. As a result, the entire temperature profile only shifts upward without changing its shape. This condition greatly simplifies the analysis of internal convection heat transfer. Mean fluid temperature variation. For constant wall temperature conditions, the mean fluid temperature approaches the wall temperature asymptotically. The difference between the wall temperature and the fluid temperature becomes smaller along the pipe. The heat transfer rate decreases because the driving temperature difference becomes smaller. However, the heat transfer process continues along the entire pipe. This behavior is characteristic of the constant wall temperature boundary condition. Heat transfer and NTU. The NTU concept is used to measure the effectiveness of the heat transfer process inside a pipe. If the NTU value is greater than 5, the outlet fluid temperature is almost equal to the wall temperature. The larger the NTU, the more effective the heat transfer process becomes. This can be achieved by increasing the surface area or the heat transfer coefficient. This concept is very important in heat exchanger design. Correct answer, B. Fluid exit temperature closely matches the surface temperature. Explanation of incorrect options. A. Minimal heat transfer between the fluid and the surface. This is incorrect because a high NTU value indicates effective heat transfer, not minimal. NTU greater than 5 signifies efficient thermal interaction. C. Reduced heat exchange efficiency along the tube. This is incorrect as a higher NTU directly correlates with increased heat exchange efficiency, reflecting a more effective process. D. Heat transfer is independent of the NTU value. This is incorrect because NTU is a critical parameter for evaluating heat transfer performance. A higher NTU signifies greater effectiveness in heat exchange. Fluid dynamics in laminar flow. Laminar flow in a pipe can be analyzed using a force balance on a fluid element. Pressure forces and shear forces balance each other under steady conditions. From this analysis, a parabolic velocity profile is obtained. The maximum shear stress occurs at the wall and is zero at the pipe center. This approach forms the basis of the Hagen-Poiseuille flow theory. Force and pressure analysis. The analysis is performed on a small cylindrical element in a fully developed flow. The pressure force along the flow direction is balanced by the shear force acting on the surface of the element. From this balance, a relation between the pressure gradient and shear stress is obtained. This equation is valid only for steady laminar flow in a horizontal pipe. The result becomes the basis for calculating the pressure drop. Pressure and head loss. The pressure loss in a pipe depends on the pipe length, diameter, flow velocity, and flow regime. This loss is often expressed as head loss to simplify energy interpretation. The general relation can be written as delta P equals F times L over D times rho times V average squared divided by 2. The friction factor F includes the effects of roughness and flow regime. This concept is very important in pumping system design.
Reducing pump power. Pump power is very sensitive to the pipe diameter, especially in laminar flow. If the pipe diameter is doubled, the required pump power can be reduced by a factor of 16. This happens because the average velocity and friction losses decrease drastically. Therefore, selecting the pipe diameter has a major impact on energy consumption. Smart design can significantly reduce operational energy costs. In laminar flow, doubling the diameter of a pipe reduces the required pumping power by a factor of 16, demonstrating the impact of diameter on energy efficiency. Energy balance in differential volume. The analysis is performed on a small cylindrical ring element inside the pipe. Heat flows radially from the wall to the fluid. The fluid temperature increases slightly along this element. The energy balance states that the heat input equals the increase in energy of the fluid mass flow. This formulation becomes the basis for deriving the temperature distribution equation inside the pipe. Fully developed laminar flow. In fully developed laminar flow, the flow properties no longer change along the flow direction. The friction factor and the heat transfer coefficient become constant. The velocity profile remains parabolic along the entire pipe length. With uniform heat flux, the radial temperature gradient also remains constant. This condition allows the use of simple analytical solutions. Nusselt and friction factor. For circular pipes, the Nusselt number has a constant value in fully developed laminar flow. For rectangular ducts, the Nusselt number increases as the aspect ratio increases. In contrast, the friction factor tends to decrease as the aspect ratio increases. The cross-sectional shape strongly affects heat transfer performance and pressure loss. Therefore, duct geometry becomes an important design parameter. Correct answer: C. Nusselt number increases with aspect ratio and friction factor decreases. Explanation of incorrect options. A. Nusselt number remains constant and friction factor is unpredictable. This is incorrect because the Nusselt number in rectangular tubes depends on the aspect ratio and does not remain constant. The friction factor also follows a predictable trend. B. Nusselt number decreases with aspect ratio while friction factor increases. This is incorrect as the Nusselt number actually increases with aspect ratio while the friction factor decreases due to reduced resistance to fluid flow in rectangular tubes. D. Heat transfer and friction are unaffected by the tube's aspect ratio. This is incorrect because the aspect ratio significantly influences both heat transfer, Nusselt number, and friction factor in rectangular geometries. Leo Gratz, contributions. Leo Gratz was one of the early scientists who made important contributions to heat transfer theory. His name is commemorated in the Gratz number, which is used to analyze thermal development in pipe flow. His work helped bridge the analysis of conduction, convection, and fluid flow. These concepts are still used today in heat exchanger analysis. His contribution shows the importance of analytical approaches in heat transfer engineering. Nusselt number in tube flow. The Nusselt number is high in the entrance region because the thermal boundary layer is not yet fully developed. For constant heat flux conditions, the Nusselt number is slightly higher than for constant wall temperature conditions. As the distance increases, the Nusselt number decreases and reaches a constant value. This value indicates that the thermally fully developed condition has been achieved. This behavior is important in determining the effective heat transfer length.
Friction factor and roughness. For smooth pipes, the friction factor has the lowest value. As the relative roughness increases, the friction factor also increases. In turbulent flow, even small roughness can significantly increase pressure losses. Therefore, the internal surface condition of the pipe strongly affects pumping energy consumption. Material selection becomes an important factor in flow system design.
Schedule 40 steel pipes. The nominal size of steel pipes is not the same as the actual inner diameter. This difference must be considered in calculating flow velocity and pressure losses. The Schedule 40 standard provides various diameter options with specific wall thicknesses. Each size has different flow capacity and hydraulic characteristics. This data is very important in industrial piping system design.
Pipe roughness values. Pipe surface roughness strongly depends on the material. Plastic pipes and some metals have very small roughness values. In contrast, concrete pipes have a very wide range of roughness. This difference causes large variations in friction factor and pressure loss. Therefore, material roughness data must always be considered in calculations.
In fluid flow applications, materials like stainless steel and brass exhibit minimal roughness, while concrete has a wide range of roughness, significantly impacting flow resistance.
Turbulent flow velocity profile. In turbulent flow, the velocity profile in the core region is relatively flatter compared to laminar flow. Very large velocity gradients occur only near the wall in the thin viscous sublayer. Most of the energy dissipation occurs in this near-wall region. This explains why wall roughness has a strong influence on turbulent flow. This structure reflects the complexity of mixing mechanisms in turbulence. Double tube heat exchanger. A double tube heat exchanger consists of two concentric pipes, one inside the other. One fluid flows in the inner pipe, while the other flows in the annulus region. Heat is transferred from one fluid to the other through the pipe wall. This configuration is simple and easy to analyze theoretically. This type is widely used for small-scale applications and laboratory experiments. Nusselt number in annulus. Flow in an annulus can be analyzed using an approach similar to pipe flow. The Nusselt number depends on the ratio of the inner and outer diameters. For the inner surface, the Nusselt number tends to be higher at smaller diameter ratios. For the outer surface, the variation of the Nusselt number is relatively small. This shows that annulus geometry strongly affects the heat transfer distribution. Enhanced tube designs. Finned surfaces are used to increase the heat transfer surface area. Roughened surfaces can increase turbulence and enhance convection. Both methods aim to increase the heat transfer rate without significantly increasing the equipment size. These techniques are widely used in compact heat exchangers and cooling systems. However, performance improvement is usually accompanied by an increase in pressure loss. Correct answer B. To improve convection heat transfer by increasing the surface area. Explanation of incorrect options. A. To reduce the surface area and minimize heat transfer. This is incorrect because fins are specifically designed to increase surface area, not reduce it, for better heat transfer. C. To enhance turbulence, increasing heat transfer efficiency. This is incorrect, as turbulence enhancement is primarily the function of roughened surfaces, not fins. Fins rely on increasing the area for heat transfer rather than inducing turbulence. D. To reduce fluid flow velocity and improve conduction. This is incorrect because fins do not focus on controlling fluid velocity or improving conduction. Their role is in improving convection by providing more surface area for heat exchange.
References. The main reference for this chapter comes from the book by Eunice A. Chengel and Afshin Gajar on heat and mass transfer. This book is one of the international standard references in the field of heat transfer. The figures and concepts used in this chapter are based on this source. A strong understanding of this reference is very helpful for deepening the subject. This literature is also widely used in research and engineering practice.